This video is going to take a look at potential energy, but do it as an example. And remember, we are talking about electrostatics at the moment. So let's do this. I'm going to give myself a setup. I'm going to say I've got this charge here, and I'm going to nail it in place. It's got a charge of, how about 40 microcoulombs, and I'm going to put a charge nearby here. Maybe I will release this guy from rest. I'm going to start it at a distance of 10 centimeters away. Let's give this a charge of half a microcoulomb, and we'll give it a mass of 1 kilogram, 2 kilograms. 2 kilograms. I want to start this thing from rest, v initial equals 0, and I want to find what speed we can get this thing moving up to. So find the final speed the object reaches. And so for that final, we're going to do this. We're going to say, here's our object, Q, mass. It is now moving at some speed, V, which is our unknown, so I'm going to put it in red. And I would like to say that the distance that it's moving, or that the distance that it is from this location, is really far away. I'm going to draw a line right down the middle, and I'm going to say over here I have potential energy that is K Q Q over R. I have kinetic energy that is 0 because I'm not moving yet. Over here I've got potential energy that is 0 because I'm getting infinitely far away from this thing, and I've got a kinetic energy that is half m v final squared. And I can set these equal to each other. And that's really all I'm doing with this. So K Q Q over R1 equals half m v final squared. Let's solve this thing for v final. I'm going to go to v final equals multiplied by 2, so 2 K Q Q. We can divide by m R1, and then I'm going to take a square root. And when I plug those values in, I get something like this. .34 meters per second. That might not sound like a lot, but I'm starting 10 centimeters away from this thing, and for electrostatics, that's a pretty big distance. If I want to look at what that charge would feel as far as a force goes, I would say my force initial is going to be K Q Q over R squared. And when I plug those numbers in, I get a force of 18 newtons. I've got a mass of 2 kilograms, which means I get an acceleration at maximum of 9 meters per second squared. Now that is something like gravity, but once I get, I mean not quite gravity, but I'm getting pretty close. Once I get out to 20 centimeters squared, 20 centimeters away, I'm doubling my distance. This number at the bottom is doubling, but that's being squared, so this is going to divide by 4. So this is at 10 centimeters. When I am at 20 centimeters, I am already down to 2.25 meters per second squared. That drops off really fast, that acceleration. We can't use our regular old kinematic equations because those were for constant acceleration. We are stuck with something a whole lot. We can't use our regular kinematic equations because those were good for constant acceleration. This is more like the gravitational acceleration, the GMM over R squared type of force, or even springs. We have to do this a different way. It turns out right away we get this acceleration that looks pretty good, and it looks promising, like this thing's going to be moving fast. But after even a very short distance, my acceleration's already dropped off quite a bit. I'm going to get up to a final speed of 1.34 meters per second. I want to do one more. What if I had that same situation, but up here I had a second charge? We'll nail that one in place too. We'll start this one 30 centimeters apart, and we're going to put a charge here. I had done half a microcoulomb before with a mass of 2 kilograms. We'll say a speed of 0 meters per second. And we'll start that one 40 centimeters away, honestly, just so that I can 3, 4, 5 triangle this thing, because it makes for a good example. The 3, 4, 5 triangle that I'm talking about is right here, right? This is 30, 30, 40. So the hypotenuse must be 50. Now how do I do this? It turns out I do it exactly the same way. My initial potential energy, I'm going to have a K Q1Q over R1 plus a K Q2Q over R2, which means I'm going to have to label some 1 and 2. So I do that, and I get something that looks a lot like this. And that is joules, just like potential energy, any energy always has been. That's all the energy I had to start with, right? My kinetic energy initial was 0. I'm saying my potential energy final is going to be 0, and my kinetic energy final is half m v final squared. I want to point out a couple of things. One, these are scalars. And the really nice thing about scalars is that I didn't have to break anything into components. I didn't have to do any kind of that work at all. I was able to just take the numbers as they were and add them together. They are just numbers. The other thing, these were both positive charges. If this one had been a negative 20 microcoulombs, then this would have had a minus sign here, and we would have been effectively subtracting 2 numbers instead. It's positive, so they just add as positives. But now I've got something that I can solve. 0.63 joules equals a half times my mass is 2 kilograms times V final squared. The 2 and the half even cancel. That was a little bit less intentional, but convenient. So my V final is going to be 0.63 joules over 1 kilogram. That was a joules. All under a square root. And that works out to be about 0.8, 0.79, sure, meters per second for my final speed. What's actually different? I had to add the effect of both of these. Both of them contributed to potential energy. And I'm going to be moving, instead of moving directly to the right, I'm going to end up moving something like that direction. I don't actually care, because I'm not looking for the final velocity, I'm just looking for the final speed. I don't care which direction I'm moving. Ultimately, all I care about is how fast am I moving. And I found that without considering any of those pieces.